Module 3, Machine Learning in Agriculture. Definition of machine learning. Machine learning uses recognized data to develop learning intelligence and create its own model, which it then uses to perform tasks. It primarily addresses classification, regression, and anomaly detection problems. Machine learning approaches are widely categorized into two types, supervised and unsupervised learning, although some literature also considers reinforcement learning as a third approach. Additionally, machine learning models continuously learn from new data, allowing them to adapt and improve over time. This adaptability makes machine learning a powerful tool for solving complex real-world challenges in fields like healthcare, finance, and technology. Unsupervised learning. Unsupervised machine learning involves training a model with data that lacks labeled outcomes. Unlike supervised learning, which relies on input-output pairs, this approach enables algorithms to independently analyze data and uncover hidden patterns or structures without explicit guidance. It is often considered more challenging than supervised learning because the model must learn to perform tasks without being directly instructed. The complexity of unsupervised learning lies in teaching a computer to achieve results without predefined instructions. This method uses domain-specific resources to identify patterns, with the quality of discovered structures assessed through a cost function. The objective is to minimize this cost function to determine optimal parameters that reveal hidden data structures. Unsupervised learning models derive their assumptions from data with unidentified characteristics. A major setback of the unsupervised algorithm is that the machine might not learn anything useful after its transformation or analysis since it does not know its destination. Common approaches in unsupervised learning. First, dimensionality reduction, reducing the number of variables in a dataset while preserving its essential information. Data is modified in such a way that it is easier to understand for another human being or another machine language. Examples: principal component analysis, PCA, T-distributed stochastic neighbor embedding, TSNE. Second cluster method. Data is classified into clusters based on similarities on shared traits. By this way, it is easier to differentiate and discover patterns. In this case, what we try to do is to learn the underlying patterns of our data. Examples include k-means, hierarchical clustering, dbScan. 3. Anomaly detection, identifying unusual data points or outliers in a dataset. Anomaly detection models learn from historical data to establish a baseline of normal behavior. They then compare new data against this baseline to identify outliers. Anomalies can manifest as point anomalies, individual data points that are significantly different from the rest, e.g., a sudden spike in network traffic. Contextual anomalies, data points that are only considered anomalous in a specific context, e.g., a high temperature in winter. Collective anomalies, a group of data points that are unusual together but may not be individually, e.g., a specific sequence of events in a system log. Supervised learning. Supervised learning is the machine learning task of learning a function that maps an input to an output based on example input-output pairs. It infers a function from labeled training data consisting of a set of training examples. Supervised learning is a type of machine learning where a model is trained using a labeled dataset. This approach involves feeding the model input data along with the corresponding correct output. The model learns the relationship between inputs and outputs and uses this knowledge to make predictions on new, unseen data. How supervised learning works. First, training phase. The model learns from a dataset containing input-output pairs. Each input is associated with a known label or target. 2. Learning process. The model identifies patterns and relationships between inputs and their corresponding labels. Third, prediction. Once trained, the model can predict labels for new data by applying the learned mapping. Fourth, evaluation. The model's performance is assessed using metrics such as accuracy, precision, recall, and mean squared error, depending on the task type. The popularly known supervised machine learning models are the decision tree, random forest, logistic regression, support vector machine, amongst others. Types of supervised learning. In precision agriculture, supervised learning plays a vital role in enhancing crop management, optimizing resource use, and improving yield predictions. Here are the types of supervised learning with examples in precision agriculture. First, classification. Classification models predict categorical outcomes, such as crop type or disease status. Crop type classification, using satellite images to classify different crop types in a field. Pest and disease detection, analyzing plant images to classify whether a plant is healthy or affected by pests or diseases. Weed detection, differentiating between crops and weeds to enable targeted herbicide application. Yield quality assessment, classifying harvested produce, e.g. fruits, into quality grades. Common algorithms include support vector machines, SVM, random forest, decision trees, and k-nearest neighbors, KNN. Second regression, DOT. Regression models predict continuous values, such as yield or nutrient levels. Yield prediction, estimating crop yield based on factors like soil health, weather conditions, and historical data. Soil nutrient estimation, predicting nutrient content in soil using sensor data. Irrigation management, predicting the required amount of water based on soil moisture and climate data. Forecasting crop prices, helping farmers make informed decisions on harvesting and selling their produce. Common algorithms includes linear regression, polynomial regression, ridge and lasso regression, and support vector regression, SVR. Supervised learning in action. 1. Image-based analysis, using drone or satellite imagery to classify crop health and predict yields. Second, sensor data utilization, applying regression models to sensor data from the field to monitor soil moisture and optimize irrigation schedules. 3. Disease management, classifying disease types from plant leaf images using computer vision models. Examples of supervised learning. 1. Random forest. Random forest is an ensemble learning algorithm that builds multiple decision trees and combines their outputs to make predictions. It is used for both classification and regression tasks. The key idea behind random forest is that a collection of weak learners, decision trees, can form a strong learner, improving accuracy and reducing overfitting. Random forest is good at handling missing values appropriately and overfitting problems. How random forest works. 1. Bootstrapping, random sampling. The algorithm randomly selects subsets of data, with replacement, to train each decision tree. This process is called bagging, bootstrap aggregating, which reduces variance and prevents overfitting. 2. Random feature selection. Unlike a standard decision tree, which considers all features at each split, random forest randomly selects a subset of features at each split. This decorrelates the trees, making the overall model more robust. Third decision tree construction. Each tree is trained independently using its subset of data and features. Trees grow until they reach a stopping criterion, e.g., maximum depth, minimum samples per leaf. Fourth prediction, aggregation. For classification, the final prediction is determined by majority voting, i.e., the class predicted by the most trees. For regression, the final prediction is the average output of all decision trees. Second decision tree, DT. DT is a supervised learning algorithm used for both classification and regression tasks. It mimics a tree-like structure to model decisions and their possible consequences, including outcomes, costs, and probabilities. A decision tree is a rule-based system used to determine actions, where each branch represents an action. It is a binary tree structure used for solving regression or classification problems, with features as internal nodes and targets as leaf nodes. The tree is constructed by traversing from the root to the leaf, making decisions at each node. The process of building the tree involves calculating the information gain, which is derived from entropy, a measure of randomness in the data. The goal is to split the dataset at each level to reduce entropy and maximize information gain with each split. In precision agriculture, a decision tree could help classify soil types or predict crop yield. For instance, the model might use attributes like soil pH, moisture content, and temperature to decide the most suitable crop to plant. Use case example, disease detection in crops. 1. Input features: leaf color, leaf shape, moisture level, temperature. 2. Tree structure. The first split might be based on leaf color, green versus yellow. Third, decision making. If yellow, the tree might further split based on moisture level to identify the disease type. Fourth outcome, leaf is classified as healthy or a specific disease category. How a decision tree works. A decision tree consists of DOT. 1. Root node, represents the entire dataset and splits into subsets. 2. Internal nodes represent tests on features, attributes of the data. Third branches show the outcomes of these tests. Fourth, leaf nodes represent the final output or prediction, class label, or numerical value. The model uses if-then logic to split the data at each node, choosing the split that results in the most homogeneous subgroups according to a chosen criterion, e.g., Gini impurity, entropy for classification, or mean squared error for regression. Key concepts. 1. Splitting, dividing the dataset into subsets based on feature values. 2. Pruning, removing sections of the tree to prevent overfitting. 3. Feature selection, choosing the best attribute to split on, using metrics like Gini impurity, measures the probability of incorrectly classifying a randomly chosen element. Entropy, information gain, measures the reduction in randomness in the data after the split. Advantages of decision trees. 1. Simple and intuitive, easy to visualize and interpret. 2. Handles categorical and numerical data, flexible with different types of inputs. 3. Requires minimal data preprocessing, no need for feature scaling or normalization. Disadvantages. 1. Prone to overfitting, especially if the tree is too deep. 2. Sensitive to data variations. Small changes in data can lead to a completely different tree. 3. Greedy algorithm. It may not always produce the most optimal tree. We have come to the end of the first part of this module. Stay tuned as we journey through the other parts.